So welcome to part 2 of lecture 5 on an introduction to the dynamics in Einstein's world. In this case, we're going to want to discuss relativistic force and energy conservation. And we'll start with a review of Newton's ideas of force, potential energy, and energy conservation, and see how they'll generalize to Einstein's world. Get used to his new ideas of relativistic energy conservation and relativistic momentum conservation. So we'll begin with forces in Newton's world. We might have gravity acting between two particles, and we know that the force there is an inverse square law, where the force is proportional to the rest masses of the two particles that are attracting one another, and that the force is attractive, and it lies on the line between the two particles. Well, we might also consider harmonic forces, so a force is equal to minus k, a spring constant, times the distance between the particles, and it acts along the line between the two particles, and it's attractive with that minus sign. Now, in order to discuss energy conservation, of course, we find it convenient to introduce potential energy. I just want to remind you of that from your elementary physics course. So we introduce potential energy, U of R, and it's introduced so that the force is minus the gradient of the potential. Okay. Then we can think about energy conservation. Okay. So we think about the work done by the force in moving it from position 1 to position 2. Right? That's the work that's done. And I'm going to try to relate the work that's done to the change in the potential energy and the change in the kinetic energy as that work acts from position 1 to position 2. So first, I'll consider the work going from 1 to 2. That's a line integral of 1 to 2 of the force dotted into the displacement. And I'm doing a one-dimensional problem just to keep things simple. And in the textbook, you know, it can be written down in vector calculus form, and you can do the general case that way. That's fine. I'm just trying to illustrate this bit of the problem. So I have to integrate up the force over a distance. In my case, that the force is conservative, that is, it's equal to minus the gradient of a potential. I replace the force by minus du by dx. Dot dx. I see the total derivative of the potential, so that integral is just u of 1, position 1 minus u of position 2. Okay. So that's a change of the potential between those 2 points. But now I can use the equation of motion and relate that to the change in the kinetic energy of the particle when the force acts between those 2 positions. So the force is equal to rate of change of the momentum. Okay? Okay, so I have to do this integral here of d by dt of p, the time rate of change of the momentum, times the displacement. But this is a particle moving, so the displacement is just the velocity times the differential in time. That's written down here. And so I have this quantity to do. And I see a time derivative of mv. Well, m is a constant, I can pull that out. Time derivative of v times v. Then I see the time derivative of v times v is just 1/2 the time derivative of v squared, so I can write that as a total time derivative. Okay, it's total time derivative of a 1/2 mv squared. That's the kinetic energy. Okay, and so the integral just depends on the kinetic energy of the 2 endpoints. It's a total derivative. It's a difference of the kinetic energy 2 and 1. I write kinetic energy as t sub 2 and t sub 1. Sometimes I'll write ke sub 2 and ke of 1, you never know. But here I'm writing it as t, following the notation in the textbook. Okay, so we learned from this the single calculation of W12 in terms of potentials and kinetic energies. And we learned that u of 1 minus u of 2, the change in the kinetic energy from 1 to 2, is equal to the change in the kinetic energy 2 to 1. So it's convenient to put the 1s on one side of the equation and the 2s on the other side of the equation, and see that T plus U is conserved. Energy is conserved. That's a total energy. Kinetic energy plus potential energy. Okay. So that's the situation in Newton's world, and we want to get the situation in Einstein's world. Okay. Well, in Newton's world, a force is equal to the time derivative of the potential of the momentum, and the momentum is just mv. Now we've learned that that's not the momentum in Einstein's world. The momentum is gamma mv. The gamma is essential there because it enforces the speed limit. Okay? Gamma goes to infinity as the velocity of the particle goes towards c, and so nothing can go faster than the speed of light. Okay? And so we try, therefore, to generalize from Newton to Einstein by just making the replacement in F equals the time derivative of the momentum by replacing Newton's momentum by Einstein's momentum, like that. So let's pursue that. Can that equation be covariant? Okay, that's the issue here. Okay, and we'll want to see that it is indeed true that the minimal change in Newton's law to Einstein is to replace Newton's momentum with Einstein's momentum, because Einstein's momentum respects the existence of a speed limit. Let's take a shot at it. We see that momentum, that Einstein, that F equals d by dt of p satisfies several conditions. In this case, then, if the sum of the forces is 0, the total momentum is conserved, and that's going to be true in Newton, and that will be true similarly in Einstein. It's just the momentum will be different between the two. But we will have a conservation law, and that's what we want, and we expect the conservation in Einstein's world to be the conservation of the relativistic momentum, because there's no hope otherwise to have a covariant equation. Okay, the formula is P equals gamma mv and E equals gamma mc squared are built with covariance in mind, as we'll see again and again. Let's take an example. Here's a little example just to get used to this equation of motion in Einstein's world. So in this case, I take a very large capacitor, 2 plates over here, and there's a constant electric field between them. Okay, and so I put a charged particle in there. The particle is accelerated. Okay, and the rate at which its momentum changes is given by Einstein's equation of motion, which is just that F is equal to the time rate of change of momentum. The force is a constant. That's because the electric field is the same everywhere across the capacitor. Okay? That's the case I'm handling. The force is a constant. So if that's the case, then it's easy for me to integrate this equation and find out what the momentum is as a function of time, what the velocity is as a function of time, and what the position is as a function of time. I'll just take it to the case of the velocity, but later in the course, we'll be interested in this example again, because actually this example has more physics in it than you might think. Okay? We'll find that this example is called what's called hyperbolic motion. Okay? That this is the solution of the question: what is the path in space-time of a particle which has a constant, which is subject to a constant proper acceleration. Okay, in this particular case, of course, the acceleration is given by the force, which is a constant across the capacitor. So this will prove to be an example of that other question, and we'll pursue it there. But let's see what we get at this point. So here I am. F is equal to the time derivative of the momentum. F is a constant. I want to integrate that up and get velocity as a function of time. Well, since F is a constant, then I see that this equation integrates up to F times the time at which over which the force is applied is equal to the change of the momentum, which is gamma mv. So I imagine the particle initially at time t equals 0 is at rest, and then the force is applied. The time over which the force is applied is called t, and so F times t is the change of the momentum, which is gamma mv. Change of momentum is the momentum at the end, minus the momentum at the beginning. The momentum at the beginning is 0, and so this is just the integral of this equation. Okay, now I can write down what gamma is. Gamma is this 1 over the square root of 1 minus v squared over c squared. In this particular case, the particle is subject to acceleration, so the velocity is a function of time, and I've indicated that in the formula. So mv is mv of t, I'll make that explicit here, and gamma is the square root, and v is a function of time. Okay, so that's fine, and now I can solve for the velocity as a function of time, given the constant nature of the force. And I've done the arithmetic to do that, okay? And I see that v of t is equal to c divided by a square root of 1 plus mc over ft all squared. Okay, and so I see, for example, two extreme cases here. I've written things in dimensionless ratios here. So if, for example, ft, the impulse, is much less than mc, right? Then this denominator here is large. Okay, the 1 is negligible, so I have downstairs the square root of mc over ft quantity squared. Square root cancels the squaring. The ft comes upstairs, and I see that v of t is f over m times t. And that's what I expect. That's just Newtonian mechanics. As long as the impulse is small compared to mc, Newtonian mechanics is a good approximation, and the velocity increases linearly with the time in the situation that the acceleration is a constant. We all know that. Acceleration is f over m. I'm just saying that v is a times t. Okay, but what's more interesting, of course, is the opposite extreme. Let's let the force be large or the time be large, so that the impulse is much larger, okay, than the characteristic impulse of the problem, which is the mass times the speed of light. If that's right, if that's the case, then this term becomes small, and the velocity approaches the speed of light from below. Okay, so again, we just see the example, okay, that at small velocities, Newton's a good approximation, but as the velocity increases, we tend to approach the speed limit. We approach the speed limit from below, and v of t approaches c from below in this particular detail. There are plots of that in the textbook, and in some of the supplementary lectures in Relativity Doctor, the website that accompanies the textbook. Okay, we discuss accelerating rocket ships, and we see that this particular example becomes more significant than you might imagine. We learn about hyperbolic motion. We learn about Rindler coordinates, and I'll refer you to that there. We'll come back to these effects later when we're segueing into general relativity, but we're not ready for it yet at this point. At this point, all I want to do is to look at this very easy case of f equals the time derivative of the momentum, and see that we get sensible results. And what could be easier than a force which is constant over space? So we see that the dynamics, at least, are consistent with postulates 1 and 2 of relativity. We've tried to build in the postulates of relativity right from the get-go. Remember that this formula for the momentum in gamma mc, was the result of requiring covariance in the context of a calculation where velocities were added by Einstein's rules, not by Galileo's rules, and so Lorentz transformations were enforced, not Galilean transformations. Okay, now we can ask, what about energy conservation? We have energy conservation in Newton's rule, in Newton's law, like here. What's the situation in Einstein's case? We want to develop some dynamics here to move to realistic problems. Okay, so again, we look at the work done as the particle it moves from 1 to 2 in the presence of this force. Again, I think that I imagine that the force is given by a conservative formula that the force is minus the gradient of a potential, and so that integral from one side can be written as the change in the potential from 1 to 2. But now, also, from the point of view of dynamics, this is I can replace the force as a time rate of change of the momentum times dx, and try to evaluate it here. In the previous case, this was a total time derivative of the kinetic energy, and in this case, I got to do a little work to see what it is. Well, d by dt of p is gamma mv, so I have to take the derivative, time derivative of gamma v, m is a constant, it can be pulled out. When the particle moves from a distance dx, that's v times dt. It's moving so at a velocity that's changing with time, but I can write it like that. Okay, and so I have to try to do this time integral. It looks a little bit tougher than before. In the previous case, gamma was 1, and I could identify v squared as the total time derivative there, but I can't do that here. I have to work a little bit harder. So I hope, however, that whatever it is on the right-hand side, that somehow it must be it will be the difference of the relativistic energies between 1 and 2, or something like that. Okay, that's what I'm hoping for, of course. Okay, I'm hoping for that. So let's bias the discussion in that direction. I remember that the relativistic energy is gamma mc squared. The relativistic momentum is gamma mv. And so the velocity that appears in this formula can be written as a ratio of momentum to energy, just taking the ratio of these two characters. And I see there's a c squared that comes along to get the dimensions right. Okay, so let's pursue that. That sounds a little bit promising. So W12 then can be written. I have a v here, that's p over e. I have dp dt and dt, okay, over here. Okay, so this v is replaced by p over e, and I leave this p alone. Let's see, so I have p dp. I could write that as dp squared, and so I get to this expression over here. Well, there's nothing I can do here unless I know how the energy changes as a function of the momentum. Well, I should be able to figure that out, because here's an explicit formula for the energy. Here's an explicit formula for the momentum. So let's see how energy is related to momentum. Let's do the arithmetic. Okay, so I take p and I square it, gamma squared m squared v squared, and I just collect terms, and it takes me just a bit of arithmetic, which I want you to do. See that the right-hand side can be written as e squared over c squared minus m squared c squared. So that's great. So there's a simple relationship between the momentum squared and the energy squared, and it's written here. E squared is p squared c squared plus m squared c to the fourth. Okay, and I've written it out in 3 dimensions, just jumping ahead a little bit. Although the illustration is in 1 dimension, it's clear how it will generalize to 3 dimensions. So this will play a very important role in everything we're going to do going forward. Okay, e squared, not saying the factors of c, e squared is p squared plus m squared. Okay. One special case here is that I could take the mass to 0 in relativity. Okay. And a particle of that variety of no mass actually carries energy and momentum. It says that E is equal to PC. That's what we said for light. Remember, that's what we said for light. So this is an observation that bears on our initial discussion of Einstein's Gedanken experiment, and we'll rederive this expression when we discuss Maxwell's equations. But here we see it coming out in general terms. If we have an energy and a momentum that are relativistic, they're related by by this energy momentum relationship that plays a very important role in everything. But now I see that E squared is equal to P squared up to a constant and added a constant. So in my previous formula where I had P squared, I can replace that by E squared over C squared, okay? Because this second term doesn't contribute because its time derivative is 0. So W12 is just this expression, okay? Okay, and then dE squared is twice E dE, okay? And so on the right hand side I get just the integral of dE, and it's perfect. It is the total time derivative of a function, which is just the energy. And so I learned that the relativistic energy plus the potential is conserved, and that's what I wanted to derive. Okay. So that shows me, at least in these special situations, okay, that I can have energy momentum conservation, and I know what to look for, and I'll be looking for more fundamental derivations of these concepts, and that's going to be the content of the next part of lecture 5, okay, which I'm going to be calling part 3 of lecture 5, where we relate the momentum and the energy to space and time.